Thanks, Gary, and thanks for inviting me here to this wonderful research center. It's a real pleasure. So today I will talk about Bayesian spatio-temporal analysis for predicting cardiac risk in the Ticino area in Switzerland, around Lugano, south of Switzerland, and for optimal positioning of defibrillators. So this is a pilot project that we aim to export also to other regions, and it's related to digitalization and society, all for social good. So I really think it does fit the theme of the workshop. So there are two main goals that we try to get out of digitalization of response to emergency calls. The first one is optimal positioning of defibrillators, and the second one is to construct a map of cardiac risk over the Ticino area that takes both into account the space and time aspects of the phenomenon that we're trying to study. So what do we really mean by smart city or smart canton and by data-driven society? Well, this is a really hard question. Let me ask you an easier question. What do you see here? Well, to me, this is really a research lab, because there's lots of data that we all produce every day when we drive, when we bike, when we walk around, carrying our smartphones and digital devices or sensors. And this, of course, creates big data. And what I will talk about today is big data for health type of application to improve our health. And specifically, I will focus on sudden cardiac death. And you might not know, but this is a very big cause of death. Covering about 50% of the death causes. These are data from the United States. And I didn't realize at first when I engaged into this project how big this was. Consider that all type of breasts cover about 30% of death causes. And what's interesting about sudden cardiac arrest is that it strikes suddenly anyone, no matter how old you are, anywhere and at any time, even if you are apparently an unhealthy person like a football player or an athlete. And those events have a huge impact not only on the family, but also on the immediate community. And potentially, they also have very high direct and indirect social costs. So let's move to Ticino, which is where I live in Lugano. Well, this is a wonderful place where to live. We have mountains, we have a lake, almost like here, water and mountains. But not only that, this is Ticino is a very good area if you decide to have an out-of-hospital cardiac arrest. Because the survival rate in Ticino, here it is, in 2016 was about 57%, which is very high. Almost as high as the 62% survival rate that was observed in Seattle. This is data from 2013. It's not really updated, but it's growing. So we are very high in survival rate. And this is because in the Ticino area, we have a large number of automated external defibrillators that it's growing steadily over time from 2005 to 2017. These are more updated data. And today I will focus on public access defibrillators mostly, that is defibrillators that are accessible for immediate intervention. And the high success rate in terms of survival in the Ticino area is also due to very high first responder answers to the Ticino Soccorso alarms. So in 2017, the response rate was over 95%. And this is also thanks to an app that I have on my phone that was created by the Fondazione Ticino Cuore, and everybody can use this app. And if you are witnessing cardiac arrest, you can use the app to locate the defibrillator nearest to you, and the app will also navigate you to the closest defibrillators, and it also instructs you how to proceed. For example, it has the proper sound at the rate at which you should do the PCR, the attempt of resuscitation while you wait for the defibrillators. And this app, of course, generates more and more data. And the model of care that is adopted in Ticino is really very effective. And of course, throughout this line that goes from the bystander who is witnessing an event, to the dispatcher, to the first responders, to the paramedic, and finally to the hospital, all along this line, we are creating more and more data. And these days, we're also talking about using defidrone, that is drones that carry defibrillators right where it's needed. So there's really a big effort in ensuring the continuity of care. And as I said, this is obtained while in the process creating more and more data through the app, through the defibrillators, and to the tools that are used also afterwards to ensure a good life status after the event. So let's get to some data. Sudden cardiac arrest strikes about 350 people in Ticino every year. 80% of the events happen at home, and the survival rate is less than 10%. 60% of the events are witnessed, so there's somebody there who could do something immediately. And it's important to have an immediate intervention, because the loss of blood to the brain starts to cause brain damage in just 4 to 6 minutes. So you might not die, but if the intervention is not immediate, you might have brain damage more severe as more time goes by. So remember this 4 to 6 minutes, because it will become important later on. So what are the data that we currently have? Well, we have the registry of cardiac arrests, the registry of acute coronary syndromes, and the app by the Fondazione Ticino Cuore that is used by the first responders. We also have the location of all ambulances, and the GPS coordinate of the defibrillators that are there in the area of Ticino. We also gather from the federal data from Ticino the registry of building and residents. We have the registry of population by gender and age. And we are including in the analysis data from Meteo Suisse, and the medical electronic folder. This is, I will not talk to you about this because this is really ongoing research, but this is where we are heading, because there is a statistical literature that shows that meteorological condition like air temperature, amount of light, and of course the pollution do affect the probability of having a cardiac arrest. So what are the research questions that we're trying to answer with this data? Well, first of all, it's important to visualize data with interactive maps. Then we want to study the average distance of events to the closest public access defibrillators. And we want to see how many events are in the range of 200 meters from each public access defibrillators. Why 200 meters? Well, it's related to the 6 minutes that I was telling you before, which is the time where a defibrillator is effective if you bring it to the person who is having the arrest. We are trying to optimally allocate new defibrillators on the territory, but most importantly also to possibly relocate existing defibrillators. So to buy a new defibrillator is more costly than to reallocate existing ones. So with a cost constraint, we try to find the most effective combination of new defibrillator and reallocating existing one. And we also want to build a map of cardiac risk over the area. So these are the type of visualization that we can produce. Here you have the percentage of coverage of events. And here are the defibrillators that are available within 50 meters, 100 meters, 200 meters, and so on. And in orange, we have the public access defibrillators. And in purple, we have all defibrillators that might not be available to public. For example, I'm pretty sure that in this building there is a defibrillator which is probably not available overnight because the building will be closed to public. So defibrillator in schools or offices or even pharmacies fall in this category, so the purple ones. So this red line is the red line that indicates the coverage that was reported in this paper that studies the area of Toronto where they have the highest survival rate. We see that within this the distance of 100 meters, we have about 25% of the defibrillators that cover events. And here is a similar plot, again orange and purple, public access and all defibrillators, dividing the events by the location, like school, work, home, and so on. And as I said, most defibrillators are not at home, while about 80% of events do happen at home. So it's important to see where defibrillators are located relative to the buildings that we get from the Federal Registry. And again, we can do a similar analysis related to urban location, for example, Lugano, which is where I live. We have a fairly good coverage both of public access defibrillator and general defibrillators. So these are the type of maps that we produce. In green, you see the defibrillators. And in red, you see the events. This is an area north of Lugano, Ascona, and this map refers to 2016. Now, from this map, it's fairly clear that those two defibrillators would be better off moved down here. Okay? Now, this is clear by looking at the map. What we try to do is to come up with an optimization procedure that does this automatically for every defibrillator with respect to the event's location. And we do that, and here you see the results. So how can we improve the coverage of defibrillators while at the same time saving money? So we save life and we save money at the same time. So on the x-axis of those plots, you have the cost of adding a defibrillators in Swiss francs. And on the vertical axis, you have the percentage of events covered. So you clearly, as you spend more money, you cover more events. Now, the three lines that you see refer to three different ways of optimizing the positioning of defibrillators. One refers to population. So this is a very simple way of positioning defibrillators. You look at population, where there's more people, you place more defibrillators. And you see that it's not as effective as an optimization procedure that takes into account not only the population, but the risk of the different areas. And if that is combined with possible relocation of existing defibrillator that costs less relative to buying a new one, you see that you're more and more effective. So at the same time, you improve the percentage of events that are covered and decrease the median distance in meters from an event to the nearest available defibrillators. So the three rows refer to urban area, rural area, and overall. So how do we achieve that? How do we optimize the area? Well, in the literature, there was a very simplistic way of considering whether an event was covered by a defibrillator. So you just take a compass, you point it into the defibrillators, you take a circular area with center in the defibrillator, and you see how many events fall in that area. Well, we tried to do something more sophisticated and more realistic. Because we cannot fly when we carry a defibrillator, we have to run along roads. So now we have Google Maps, and we use that. So we construct catchment areas that are not circular, but have a shape that you can see here that is very irregular, and we get those shapes by actually looking at how far a person that walks at a fairly fast speed, 1.5 meters per second, can run in 3 minutes. Remember, 6 minutes is the time where it is effective to have a defibrillator, so 3 minutes to go, 3 minutes to come back. So that would make 270 meters. We include time for alarm, recruitment, and use of the defibrillator. So instead of 270 meters, realistically, we look at areas of 200 meters that we can actually run along streets. The isochrones that we construct have an average area of 36,000 square meters that correspond to a circular area of 107 radius meter, a circular one. So within this area, we cover about 30% of arrests, events that we have witnessed in the past. So we compute the number of out-of-hospital cardiac arrests, so this is the acronym for out-of-hospital cardiac arrest, falling inside catchment areas that are thus eligible for an effective use of the defibrillator. And with the circular areas, the coverage is surprisingly less. It's only 21%. With those isochrone is about 30%. And those are the absolute number of events that we can cover. And so we have, on one hand, an analysis of the demand of defibrillators, which has a high granularity because we consider not only the resident population, but we also include their characteristics in terms of age and gender. Those are two covariates that do affect the probability of having out-of-hospital cardiac arrest, actually a cardiac arrest in general, regardless whether it's out of hospital or not. The deployment strategy that we use is crossing the supply and the demand, and we have a plan for positioning new defibrillators or moving existing defibrillators. So in this map, in blue, you see defibrillators that are not displaced, that were there and remain there even after our optimization strategy. In red, you see the defibrillator that we decide to move, and in green, the new defibrillators. So given a certain amount of money, we decide how many defibrillators to relocate, how many defibrillators to buy. And in this map, the yellow star are all the defibrillators. This colored, I don't know, is the events. And then you see the areas. So how much do we improve by using this new deployment strategy? Well, we go from a coverage of 30% to a coverage of almost 44% of the events. And here is how the iterative algorithm works. So we take into account the demand and the supply, and we look at the cell with the highest risk score. We look at the defibrillator with the lowest efficiency score, so with the smallest number of events in that area, and we compute the ratio between the performance gain and the cost for a new purchase, so a new defibrillator. And at the same time, the ratio between the performance gain and the cost for displacement of an AED. And we decide which one of the two is best to perform, buy a new one, relocate an existing one, and we iterate and we find an optimal point. So this is the end of the first part of my presentation. The second part is about how we construct risk map for cardiac arrests. So here we use the integrated nested Laplace approximation, which is a Bayesian methodology used for prediction of cardiac arrest in each of the 119 municipalities. The covariates that we use are the population with gender and age distribution. And we distinguish cardiac arrest by different features, whether the resuscitation was attempted, whether the event was witnessed, and whether the event was shockable. Shockable means if with a defibrillator, the arrest reacts to the fact that we apply a defibrillator. Some of the events are non-shockable. So even if we bring a defibrillator, it's of not much use. We have a training sample from 2005 to 2015. We use 2 years for validation, and we predict what happens in 2018. We are now gathering the data for 2018 to check how good our predictions are. So this is a spatial-temporal model. YIT is the number of out-of-hospital cardiac arrest at a certain municipality, I. We have 119 municipalities, and at a certain year. We have 10 years of data that we use to train our sample. And the expected number of events is obtained by multiplying an incident per unit of population. This is mu IT over time. And that is multiplied by the overall population in that cell I at time t. And the overall incidence has 6 components. We have an overall risk. We have the effect induced by demographic features that are age and gender. We have a spatial component due to the geographic heterogeneity of the area, a temporal component, and a spatial-temporal component. So more formally, here's the model. The number of events is modeled as a Poisson distribution, and the log of the rate as an overall risk, an age and gender effect. Then we have a spatial component, a temporal component, and a spatial-temporal component. And being Bayesian, and then we have whatever is left, a non-structural component. And being Bayesian, we have some prior distributions on the overall risk and on the age and gender parameter. And then the spatial component is modeled as a Gaussian distribution centered at the average value of that variable in a neighborhood of that variable. So how do we estimate this model? Well, Bayesian computing is very effective, but is not good to solve many computational issues. In particular, MCMC sometimes is slow, especially for hierarchical models, as the one that we are using in this setting. And this is why we resort to INLA, integrated nested Laplace approximation. So INLA do approximate Bayesian inference for a specific class of model, which is the latent Gaussian model. And within this class, INLA is faster and more accurate than the MCMC tools. So INLA cannot do all models, but the models that INLA can do does very well. And this latent Gaussian models is a very rich class of models, and in particular includes generalized linear models, GLM, and generalized linear mixed model, and generalized additive models, and generalized additive mixed models, which is a very, very rich class of models. So INLA is very much used in the world. There's more than 25,000 users, so it's a little advertisement about INLA. 25% of them are in the States, many in the UK, so this is a map of users of INLA. So what are the ingredients that are needed for estimating with INLA? Well, there's a Gaussian Markov random field, a latent Gaussian model, and it uses Laplace approximation, so second order Taylor expansions. And what is a Gaussian random field? Well, I think I will not go into the details, but of INLA. Just take my word for it. I've done MCMC for many, many years, but for this type of models, I think INLA is more effective. So let me show you the results. So our model does fit into the INLA framework. And as I said, INLA is very convenient if you have a Gaussian Markov random field of large dimension with a highly sparse structure. And we are in this setting. But still, the dimension of the hyperparameter space is fairly small. So in this setting, INLA is very fast, very accurate in terms of relative error, and does have good scaling properties when we have big data. And our model does fall into this setting, and these are the type of maps that we can get when using INLA with our data. So this is the Ticino area, and this is the, for year 2016, the prediction map. So as I said, we use the data until 2015 as training data, and then we can predict what happened in 2016. We actually do have the data for 2016, and the maximum error that we make in absolute terms is 7. So there is one of those 120 cantons, municipalities, sorry, where we make an error as high as 7, but most of the time we get it exactly right. So we can predict the exact number of events in each municipality. And this is the R squared. So over the training sample, we have an R square of about 85 to 90%. Over the test sample, of course, the R square goes down, but is still fairly high, about 80% over the validation set. And we can verify whether there are municipalities that do have different incidence So whether the spatial component that we take into account is actually there. And here are two municipalities, the black one and the red one. And you can see with the credible intervals do not overlap over the entire period. And here is a rank of the two municipalities. One has a very high incidence, one has a very low incidence. On the other hand, there are municipalities where there's no effective difference. Here the two credible intervals do overlap, and municipalities where they do overlap at the beginning of our observational period, and then the incidence does diverge. And this is very important because for deployment of new defibrillators in different areas, we now take into account the differential risk that different areas do have in terms of probability of having events. So, as I said, we are now looking at geographies other than Ticino. For example, we are trying to go to the Lombardia area, which is right across the border, north of Italy, and we're trying to do a similar analysis. We are trying to now enrich the model with meteorological and environmental covariates. And something else that INLA allows us to do is to take into account natural barriers. So municipalities that are separated by mountains affect each other at a lesser extent. And in Ticino, we have a wonderful lake. We do have mountains and valleys. Right now, we're not taking into account those barriers, but INLA does allow you to do that. There's a latest, and we're also extending to other type of cardiac events. So this is a big project in collaboration with, in alphabetical orders, a lot of people, somebody also from Queensland University of Technology, a PhD student who came to Lugano to visit us. Here are foundations that did support our research by providing either financial support, like Fondazione Fratelli Agostino and Enrico Rocca, or providing data, like Fondazione Cantonale Ticinese Servizio Ambulanze and Cardiocentro and Università della Svizzera Italiana. So it was a big effort. And there are still open questions, and we're working on that. Thank you.